Welcome back to Physics for Life Scientists. The only problem is that this chapter on circuits is not a favorite for life scientists. The connections with the biological world are a little bit harder to find, but I did my best to offset that for you by hiding, not really hiding, but just putting little doses of biology, amusing, funny, interesting doses within the module to kind of break up all the physicsy stuff that we'll be learning this chapter. But for those of you who just love the mathy physics stuff, you will love this chapter on circuits. All right, let's get going. So if you would go to the Quote of the Week slide, I decided to do something kind of interesting this week. And I've never done this before, and I'm excited to see the results. And the Quote of the Week is the you quote. If you were to make a quote that a professor hundreds of years from now put on his or her Prezi, what would it be? What would it be? So here's the thing. You all have been in this rodeo of life for, between 18 and 40 years. Sorry if I missed anybody. But so there's a certain amount of wisdom that you all have gleaned from this life. And so if you were to, make a quote that's based on any learning, maybe the wisest quote that you could come up with as a human being based on everything that you've learned so far on this planet, what would it be? It's not a required assignment, but if you come up with something that you feel like is helpful and useful, I would love for you to send it to me in an email. And if I get enough, I hope to make a little announcement or like a little page that has all the wisdom gathered from our own class. All right, looking forward to it. So send that over if you have some wisdom from life. And the truth of the matter is, I know all of you have at least some wisdom that you've gained from this time on the planet. All right, why do we care? The biophysics of pacemakers. So one of the obvious examples of a biomedical application of circuits is that for folks that have a hard time with their heart beating on its own, we have a circuit fixed with its own battery that is constantly providing electric signals to the heart so that it keeps beating at the right rate. All right. So for those of you who are interested in this, this will become a little bit more clear over the course of this lecture. But I definitely encourage you to explore the biophysics of pacemakers, which is both in the textbook and there are plenty of videos on the YouTubes. All right. So this chapter is about looking at the most basic, the most foundational physics of circuits. And while circuits don't have a heck of a lot of applications in the biomedical world, aside from the machinery that biomedicine uses relies on circuits to a large degree, but while that may not be the main thrust of this chapter, what I want to convey is everything that we get to enjoy in terms of modern technology requires some kind of a circuit. And what is a circuit? It's really a source of voltage, right? Usually called a battery, and several resistors, which are just things that use the energy stored in that battery. Now, those resistors could be little resistors that are just designed to make the current what it needs to be in a certain section of that circuit, or a resistor is something that you actually use in life, like a light bulb or a hair dryer or your phone when you're plugging it in and charging it, or this screen that's illuminating me right now, or your computer if you're charging it, or your television, right? Resistors are anything in a circuit that uses that energy. Now, the thing is, that's everything, right? That's everything that we plug into a wall and use. That's almost every toy that we get or receive when we're a kid. Anything that you have to put a battery in, a flashlight, right? These are all basic circuits, and so there's really no end to how significant they are and how much they're used in the course of human life. Okay, so we're going to start by just talking about two different types of circuits. Okay, the first type of circuit that I want to discuss is the series circuit. That's the easiest circuit. It's the simplest circuit. All right, and there's very few actual series circuits in terms of what we use in the world. They tend to be more complicated than this, but sometimes a flashlight, I suppose, is just a series circuit. Now, a series circuit is simply a circuit, this is a battery, where there's no junctions, no place where the circuit breaks off. You can basically, you have a series circuit if you can trace the entire way around it without lifting your pencil off the paper. Okay? So notice there are no junctions here whatsoever. There's really only one possible path that the circuit could take. That's the essence of a series circuit. There is only one path that it could take around the circuit. All right? Does that make sense? So how is that different than, let's say, a parallel circuit? Well, I'll show you. So a parallel circuit looks like this. I always forget if there's two R's in parallel. I don't know. Okay, so a parallel circuit will look like this. You have multiple paths that an electron can take, okay? So whereas in the series circuit, if I were a little electron that left the circuit, right? Yeah, so yeah, let's say I'm a little electron that leaves the circuit, okay? So I would go around here, and there's no choice for me. There's no choice for me to go anywhere else, right? But if I was a little electron over here, I start cruising along. Oh, I'm a little electron, right? And he reaches this little junction, okay? This little electron reaches this junction, and suddenly the electron has a choice. It could go this way, or it could go this way, right? And then let's say it does decide to go this way, right? Then the electron's over here. It has a choice again. It could go this way, or it could go this way, right? So in a parallel circuit, the electrons have to make choices about which direction they're going to go, right? Whereas in a series circuit, there's only one option, one single loop, okay? Another way to think of the difference is parallel circuits have what are called junctions, okay? So junctions happen whenever there's at least 3 different wires reaching one single point, okay? Here, that never happens, right? There's these corners, but that's not a junction, right? It doesn't break off into another direction, right? There's just one little possible loop, but parallel, there's these junctions where at those junctions, electrons have to make choices, all right? That's the difference. That's the difference. So these are the two kinds of circuits that we have. Now, in our homes, we focus almost exclusively on parallel circuits because, you have one source of power coming in, right? And you have all these different plugs, right? Each of these plugs represents another junction in a parallel circuit inside of our homes. All right. So I hope that's clear, this distinction between series and parallel. And with that said, I want to talk a little bit about how you add resistors. Here I have 3 resistors in the circuit. I have 3 resistors in this circuit. How do you add resistors in series and parallel? Okay. Well, we're going to talk about series first. So adding resistors in series, honestly, it's truly, truly easy. It's a piece of cake. It's just adding. You know how to do that, right? Yeah, I thought so. Okay, so it's just adding. So in other words, so if I want to like turn this into another circuit with an equivalent resistance, right? I want to turn all 3 of these resistors, we're going to call this one R1, R2, and R3, right? If I want to turn this into just one resistor, an equivalent resistor, this T means total resistance, right? Then all I got to do is add R1, R2, and R3. It's simple. So R total is equal to R1 plus R2 plus R3. And if there's more resistors, then dot, dot, dot. Okay? Pretty basic, right? So if this were 1, 2, and 3 ohms, respectively, then it would be 1 plus 2 plus 3 is 6. That might be the easiest thing you learn all semester, and you're welcome. Okay, a little bit more complicated is adding resistors in parallel. So let's try that. What does that look like? Okay, so if I go over here and draw a little parallel circuit, I have 1 resistor, call it R1, 2 resistor, R2, 3 resistor, R3, right? And again, I want to I want to replace all this with one equivalent resistance. Is that getting squeakier? I think so. All right. So if I want to find this, this is how we do it. This is how we add it. Okay? It's a little bit weird, but again, you're pretty smart. This is math you could do. So 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay? All right, so let's give an example of how you would add that. So I'm adding these in parallel, right? Once again, let's say that this is 1 ohm, this is 2 ohms, this is 3 ohms. Okay? All right, so in that case, 1 over the total resistance would be 1 over 1 plus 1 over 2 plus 1 over 3, right? Now, as you know, with adding fractions, oh, please tell me you remember how to add fractions. I hope so. But if not, here's a little refresher. You want to find a common denominator, right? So what would be a good common denominator of 1, 2, and 3? I would probably pick 6, right? 6, 2 and 3 are both multiples of 6, right? Okay, so that would turn into, and I'm going to start writing it over here, that would be 6 over 6 plus 3 over 6 plus 2 over 6, right? I'm basically just multiplying this by 3 over 3 and multiplying this by 2 over 2 to get the common denominator, okay? And I add these up. So remember, this is 1 over RT. I add these up. I get 6 plus 3 is 9 plus 2 is 11. I get 11 over 6, right? But is that our answer? No, it's not our answer because this is 1 over RT. So to get the actual RT, you just have to take the reciprocal of both. You flip them, right? So this would be 6 over 11 ohms. Okay? The first thing that I want you to notice is that when you add resistors in parallel, you end up getting a smaller number. 6 over 11, that's not even 1, right? That's just a little over a half, okay? But all these resistors are 1, 2, and 3. So adding resistors in parallel, you actually get a smaller resistance. Whereas when we added resistors in series, 1 plus 2 plus 3 equals 6, you get a bigger resistance. Take note of that. It's a good way to check your work if you're adding resistors in parallel. If you get an answer that's bigger than your resistances, then you know you've done something wrong. Okay? All right, there it is. That's how to do it. Now, we are obviously going to have examples where they're much more complex than this. All right, more complex circuits with a mixture of series parts and parallel parts. How do you add resistances then? In the next video, we're going to do a few examples. I'll see you there.